Well, hello there fellow introverts and welcome back to the channel. Today we have another topic that was voted on by you, the viewers. So, we're going to learn how to travel through space. Space travel. So if you are like me and you've ever wondered if a crewed spacecraft could be built to travel at or near the speed of light, how long would it take to achieve that speed without crushing human occupants, right? That's a normal thought that we all have. No? Just me? Oh, alright. However, despite what science fiction may suggest, humanity will never be able to travel at the speed of light. That said, we could theoretically get close. To cause the fewest problems for our human occupants, it would be best to maintain the acceleration our body was familiar with. Earth's gravitational pull at the surface of our planet, that is 32.2 feet per second squared, or about 9.8 meters a second squared. Accelerating at the rate from the perspective of the traveler, it would take 2.65 years to reach 99% speed of light. To better appreciate this result, consider that such as a traveler wants to reach the center of the Milky Way. That's nearly 30,000 light years distance. For half that distance, they want to accelerate at 32.2 feet per second squared, and then decelerate by that same amount for the remaining half of the journey. At that acceleration, it would take the traveler around 20 years to get there, 40 years for a round trip. But some weird things happen to time when moving close to the speed of light. While only a few decades have passed for the traveler, significantly more time will have passed on Earth. Let's assume the impossible. The traveler manages to travel at the speed of light the entire way. In that case, nearly 30,000 years will have passed on Earth by the time they reach the center of the galaxy for the round-trip journey. 60,000 years will have gone by at the end from the Earth's perspective. Needless to say, the traveler's friends at the time of departure would no longer be around when they return. The difference in observed time, or time dilation, is the consequence of Einstein's special relativity and illustrates his famous twin paradox. And again, we all know what Einstein's special relativity is and the twin paradox. But, for those who don't, I'll go ahead and explain it to you. Maybe. Now, pay attention, because there will be a quiz. Now, Einstein's special theory of relativity, also known as special relativity for short, is a fundamental theory in physics proposed by Albert Einstein in 1905. It revolutionized our understanding of space, time, and the relationship between matter and energy. Special relativity provides a new framework for describing the laws of physics when objects are moving at constant speeds relative to each other, particularly at speeds close to the speed of light. There are a few key principles that outline this theory. First is the principle of relativity. The laws of physics are the same in all inertial reference frames. An inertial reference frame is a frame of reference that is not accelerating. So, when the parent is standing in the store and the child is running away, inertial frame of reference. The consistency of the speed of light. The speed of light in a vacuum is constant and is the same for all observers, regardless of the motion relative to the source of light. This means that the speed of light is the absolute speed limit in the universe. Time dilation. Time can appear to run at different rates for observers in relative motion. An object in motion experiences time dilation, meaning its eternal clock appears to run slower from the perspective of the stationary observer. Objects moving relative to an observer can appear shorter along a direction of motion. This phenomenon is called length contraction. Realistic mass and energy equivalence, special relativity, introduces the famous equation E equals mc squared, which we all have heard of and seen. It's probably on a poster in your science classroom right now. Where E represents energy, M represents mass, and C represents the speed of light. It shows that mass and energy are interchangeable and that the small amount of mass can be converted into a large amount of energy. These principles are profound implications for various aspects of physics, including the behavior of particles at high speeds, the nature of space-time, and the concept of simultaneity. Special relativity has been extensively tested and confirmed by numerous experiments and observations, and forms the foundation of modern physics, particularly in the fields of particle physics and astrophysics. So, that being said, blame Albert Einstein for limiting us on our ability to travel faster than light in a vacuum. Now, the other part of this is Einstein's twin paradox. Is a thought experiment from the principles of special relativity. Now, it explores the concept of time dilation and the effects of relative motion on the aging process of individuals. The paradox involves two identical twins. One stays on Earth, the stationary twin, and the other travels into space at high speed in a spacecraft, the traveling twin, respectively, before returning to Earth. According to the principles of special relativity, time appears to run differently for the traveling twin compared to the stationary twin due to their relative motion. From the perspective of the stationary twin, time passes at its normal rate, while the traveling twin experiences time dilation. This means that the traveling twin's clock appears to run slower relative to the stationary twin. As a result, when the traveling twin returns to Earth after their journey, they would be younger than the stationary twin. The paradox lies in the apparent asymmetry of aging. According to the stationary twin, they remained in a constant reference frame and experienced time normally. However, the traveling twin underwent acceleration and deceleration during the journey, which introduces a difference in the frame of reference. When they reunite, the traveling twin would have experienced less time compared to the stationary twin. The twin paradox is often used to illustrate the concepts of time dilation and the relativity of simultaneity. It highlights the effects of relative motion on the flow of time and challenge our intuitive understanding of time as an absolute quantity. In reality, the paradox is resolved by considering the acceleration of the traveling twin, which breaks the symmetry between the two situations and leads to the observed age difference upon reunion. Now, that's all well and good, but that's a lot of jargon. Does that really mean anything? The short answer is, yeah, it does. And what it means, you see, when an object with mass, like a spaceship or even human, accelerates toward the speed of light, something peculiar happens. As it gets closer and closer to this incredible speed, its mass appears to increase. It's like trying to push a heavy ball that becomes heavier and heavier as you try to make it move faster. Or how heavy your body gets after Monday. Tuesday it's a little bit heavier, Wednesday, Thursday, Friday, so on. The more we try to speed up, the more energy we need. And as we approach the speed of light, the energy required becomes infinite. It's as the universe is telling us, no, you can't go that fast. But if the spaceship had Red Bull, then potentially. Now, a word from our sponsor. Subscribe to survive. Please. It was me. I'm the sponsor. I sponsor my own videos. Okay, awkward. But that's not all. As we near the speed of light, strange things happen to time and space. Time starts to slow down and lengthens in the direction of motion starts to shrink. This is, as we spoke before, called time dilation and length of contraction. So even if we could have somehow overcome the infinite energy problem with a Red Bull, our journey would become a slow motion experience and the world around us would appear squished. But there's one more obstacle standing in our way. Probably Bill Gates. A fundamental principle of the universe states that the speed of light is an absolute speed limit. Nothing with mass can travel faster than light. So, this means that no matter how hard we try, we can never reach or exceed the speed of light. It's like trying to catch a beam of light in your hands. You just can't do it. Unless you're a Jedi, or Mr. Miyagi. So while traveling at the speed of light might be a thrilling idea, our current understanding of physics tells us that it's impossible for objects with mass, including us humans. The universe has its own rules, and the limit of light reminds us that some frontiers are meant to remain unexplored. I know you're like me and you're brokenhearted that we can't travel through time. The concept of time travel is primarily explored within the framework of theoretical physics, specifically through the theory of general relativity proposed by Mr. Einstein. While time travel remains speculative and unproven at best, there are some theories that suggest the possibility of traversing time. But you're saying there's a chance. One of the theories that has gained attention was the concept of wormholes, or Einstein-Rosen bridges. According to general relativity, space-time can be curved and distorted, allowing for the existence of wormholes, a hypothetical tunnel that connects two distant regions of space-time. It has been suggested that traversing through the wormhole could potentially create a shortcut, enabling travel between different points in time as well as space. However, significant challenges and unknowns remain, such as the stability and the practicality of wormholes, as well as the need for exotic matter with negative energy to keep the wormhole open. Now, for those of you who don't know what a black hole is, by definition, a black hole is a region of space-time exhibiting gravitational acceleration, so nothing, not even light, can escape its gravitational pull. Black holes are formed when massive stars undergo gravitational collapses at the end of their life cycle. This collapse results in an incredibly dense object with a strong gravitational field. Now, black holes have a boundary called the event horizon, which is the point of no return. Once an object crosses the event horizon, it cannot escape the black hole's gravitational pull. At the center of a black hole lies a gravitational singularity, a point of infinite density and zero volume, or current understanding of our physics breaks down a singularity. So we're just guessing at what's at the center. We don't really know. Just because of the logistics of it, can't necessarily just like walk to it. Nobody wants to throw like $1 billion satellite into a black hole. I mean, it's not my satellite, so I'd do it, but you know, whatever. Black holes are classified based on their mass. Stellar black holes have a mass several times that of the sun, while supermassive black holes have millions or billions of solar masses and are found at centers of galaxies. Stephen Hawking, remember that guy? Proposed that black holes can emit a type of radiation now known as Hawking radiation. This radiation results from quantum effects near the event horizon and causes black holes to slowly lose mass over time. Black holes present a theoretical challenge known as the information paradox. According to quantum mechanics, information should never be lost, but it seems to disappear when objects enter a black hole. Resolving this paradox is an active area of research. Now, the problem with trying to gauge black holes is there's several different types and they all act differently. They're relatively the same, but just different enough to make the nerds uncomfortable. So, the first type, stellar black holes are formed from the gravitational collapse of a massive star. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion and the remaining core collapses under its own gravity, forming a black hole. Stellar black holes typically have the mass ranging from a few times to 10 times of that of the Sun. Intermediate black holes are hypothesized to have masses between stellar black holes and supermassive black holes, which is why they're intermediate. Their formation mechanics are not yet well understood, but they could form through a gradual accumulation of mass in dense stellar clusters or through the collision or merger of smaller black holes. Now, the big daddy, supermassive black holes, are extremely massive, as the name implies. Some would say they're super massive, with millions or even billions of times that the mass of our sun. They reside at the centers of most galaxies, including our own Milky Way galaxy. The exact mechanism for their formation are still subject to active research, but they may form through the accretion of mass and the merging of small black holes over cosmic time scales. Primordial black holes are hypothetical black holes that could have formed in early universe, shortly before the Big Bang, and these black holes would have formed from fluctuations in the density of matter during the universe's infancy. Primordial black holes could have a wide range of masses, from tiny ones with mass of an asteroid to larger ones with the mass of a mountain or more. Micro black holes are another hypothetical type of black hole. These black holes would have very small masses, possibly even smaller than an atom. They are predicted by some theories as a certain model of extra-dimensional or the formation of black holes in the early moments of the Big Bang. However, micro black holes have never been observed or confirmed to exist. And also, it is worth noting that our current knowledge of black holes is based on theoretical models and observational evidence, and ongoing research continues to deepen our understanding of these enigmatic cosmic objects. While we've listed the different types of black holes that are limited by understanding, but now with that, they act differently. The gravitational pull of black holes is directly related to its mass. Naturally, stellar black holes are relatively strong gravitational pull compared to their size, while supermassive black holes have an immense gravitational pull due to their enormous mass. The gravitational pull of black holes determines its effect on nearby objects and the distortion of space-time around it. The accretion disk, when matter falls towards a black hole, it forms an accretion disk, a rotating disk of gas and dust that spirals around the black hole. The properties of the accretion disk, such as temperature and luminosity, can vary depending on the mass of and rate of accretion onto the black hole. Supermassive black holes typically have a larger and more massive accretion disk compared to the stellar black holes. Some black holes, especially those with accretion disks, can emit powerful jets of energetic particles, and these jets are observed in active galactic nuclei associated with supermassive black holes. Stellar black holes can also produce jets when they accrete matter from the companion star, although on a smaller scale than their bigger cousins. Now, the size of the event horizon, the boundary beyond which nothing can escape, the black hole's gravitational pull, varies depending on the black hole's mass. Stellar black holes have relatively small event horizons, typically a few kilometers in radius. In contrast, supermassive black holes have event horizons that can extend for millions or even billions of kilometers in radius. Now, this is what we're talking about: time dilation and spaghettification. As objects approach the event horizon of a black hole, they experience extreme gravitational time dilation. Time appears to slow down for an outside observer, while the infalling object, time seems to proceed normally. Additionally, tidal forces near the event horizon can cause a process known as spaghettification, where the immense gravity stretches and distorts objects into long, thin shapes, which is how we get string theory. Now, according to string theory, fundamental particles are not point-like structures, but tiny, vibrating strings. These strings exist in space-time that extends beyond the familiar 3 dimensions of space and 1 dimension of time. String theory postulates that there are an extra dimensions, typically 10 or 11 in total, beyond the 4 we directly experience. Superstring theory incorporates supersymmetry, a theoretical symmetry that suggests even known particles such as superpartner with a different spin properties. Supersymmetry helps resolve certain mathematical inconsistencies and provides a framework for unifying particles and forces. String theory also provides a potential framework for reconciling gravity with quantum mechanics. It suggests that the graviton, a hypothetical particle mediating the forces of gravity, is a manifestation of the vibrational modes of strings. These vibrational patterns of strings gives rise to different particles and their properties, such as mass and charge. These specific vibrational modes determine the particle's characteristics, giving rise to the rich variety of particle observed in the universe. String theory also allows the possibility of multiverses, where multiple universes with different physical properties can exist. Additionally, to explain why we observe only one spatial dimension, string theory proposes that the extra dimensions are compactified or curled up at extremely small scale, making them difficult to detect. String theory aims to unify all fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single coherent framework. It suggests that these forces arise from different vibrational patterns of strings. Now, like everything else that we spoke about today, string theory is a complex and mathematically intricate theory that is being developed. It faces various challenges, including the selection of the specific vacuum state, that matches our observed universe and the lack of direct experimental evidence. Nevertheless, research in string theory continues, exploring its mathematical properties, implications for particle physics, and connection to other areas of physics such as black holes and cosmology. Again, what does all this mean? Well, it means that we can't necessarily drive fast enough to skip through time for traditional time travel as we would like to theorize. Now, the only other way would be to jump through wormholes, which technically, like wormholes, are black holes, so this is what we're left with: the Einstein-Rosen bridge theory, also known as wormhole. It is a concept derived from the equations of general relativity by Albert Einstein and Nathan Rosen in 1935. It proposed the existence of hypothetical shortcuts or bridge that could connect two separate regions of space-time, potentially allowing for faster-than-light travel or a connection between distant parts of the universe. In general relativity, the geometry of space-time can be distorted by massive objects, causing curvature and the bending of light. Think of a blanket with different masses sitting on it, how they bend. The idea of the wormhole is based on the notion that this curvature can be manipulated to create a tunnel-like structure that connects two separate points in space-time, which we've learned is the fourth dimension. The Einstein-Rosen bridge is a specific solution to these equations of general relativity and describes a wormhole. It is named after Einstein and Rosen, who first explored this concept. The bridge is essentially a shortcut or a tunnel that connects two different regions of time. A wormhole typically consists of a throat region connecting two mouths or entrances. The throat is the narrowest part of the wormhole and acts as a conduit between the two mouths. The mouths themselves can be located in different locations or even different universes. Additionally, a wormhole may have event horizons, similar to black holes, which marks a point of no return for anything entering the wormhole. One of the major challenges with the wormholes is their stability and transversability. Theoretical calculations suggest that wormholes are inherently unstable and tend to collapse or become unusable for practical purposes. This would require exotic forms of matter or energy with negative properties, often referred to as exotic matter. Reaching real deep for these names, guys, to stabilize and keep them open for traversing. Even if stable wormholes were possible, they would likely require vast amounts of energy, create, or sustain. Moreover, the theory suggests that if a wormhole could be traversed, it might introduce complications such as violations of causality, leading to potential time travel paradoxes. Resolving these issues remains a topic of ongoing research and speculation. It's important to note that while the Einstein-Rosen bridge theory is an intriguing concept derived from general relativity, its practical realization and existence in nature are highly speculative. Further research and theoretical advancement are necessary to fully understand the nature and potential implications of wormholes in the universe. And now that you've heard me ramble on for an insurmountable amount of time, and sorry I can't help you to get this time back. But that is all I have for you nerds today, so I'll put up another poll and you can tell me what else you want to hear me ramble on about. And I'll see you nerds later.